Black holes in space are some of the most mysterious and powerful objects in the universe. Explaining black holes fully is no easy task, but astronomers are constantly developing new theories to understand the strange phenomena they create. For instance, Einstein's theory of relativity helps explain the slowing down of time near a black hole. However, this theory doesn't work at the singularity, the very center of a black hole. In this latest episode of Space Documentary, we're diving deeper into the fascinating world of black holes. Check the comment section for a link to the previous video, where we explored how stars end their lives, explode as supernovae, and become the seeds of black holes. For thousands of years, our understanding of the universe has evolved dramatically. Initially, we believed Earth was the center of everything, with the sun and stars revolving around us. This idea was upended by Copernicus, who showed that Earth and the other planets actually orbit the sun. Later, we discovered that our sun is just one star in the Milky Way galaxy, which itself orbits a mysterious supermassive black hole at its center. Galaxies, vast collections of stars, gas, and dust, are held together by gravity. While we understand the basic balance of forces at play, we still don't fully grasp why galaxies exist or how they form. Through careful observation, we've learned that galaxies have certain consistent properties that hint at their strictures and eventual fates. We can classify them based on their appearance, even if their origins remain a mystery. The most recognizable type of galaxy is the spiral galaxy. These galaxies resemble flat, rotating disks filled with stars and gas. A typical spiral galaxy contains around 100 billion stars, along with a significant amount of gas, distributed across a region about 50,000 light-years in diameter. The stars and gas within these galaxies follow circular orbits around the center, with gravity and centrifugal force in a delicate balance. For instance, it takes our Sun about 200 million years to complete one orbit around the center of the Milky Way. If an observer from a distant galaxy were to look at the Milky Way, they would see a vast, disk-like structure with the Sun located roughly 2/3 of the way out from the center. Similarly, the Andromeda Galaxy, our nearest large neighbor, lies about 2 million light-years away. It mirrors the Milky Way in size and structure, containing a mix of old and young stars as well as large quantities of gas. Spiral galaxies vary widely in size and mass, with some being 10 times more massive than others. Interestingly, spiral galaxies are not the only type we observe. There are also elliptical galaxies, which appear as more rounded, elongated shapes, and irregular galaxies, which lack a defined form. Elliptical galaxies are fascinating, massive clusters containing anywhere from 100 million to a trillion stars. Each star follows a complex path shaped by the galaxy's overall gravity. The smooth look of an elliptical galaxy tells us that these stars move in highly random orbits. This randomness, balanced with gravity's pull, keeps the galaxy stable. In most galaxies, you won't see individual stars because they're so spread out. Throughout the galaxy's 10 billion-year lifetime, stars rarely collide or come close to one another. This holds true for both elliptical and disk galaxies. Only in the incredibly dense centers of galaxies might stars collide, sometimes creating black holes. Elliptical galaxies might not be as photogenic as spirals, but they come in a variety of shapes, from nearly circular to very stretched out. This range is partly due to their actual shapes and partly because of the different angles from which we see them. Astronomers classify galaxies by their shapes, with over 100 categories developed by Gerard de Vaucouleurs. Most galaxies are either disk or elliptical, though many disk galaxies have a central bulge, and some ellipticals have faint disks. A refined classification considers the prominence of these components. The Sombrero Galaxy, for instance, has a noticeable balance of both disk and bulge, similar to most disk galaxies with varying bulge sizes. Disk galaxies have cool gas and young stars, while elliptical galaxies don't have either. This is an important clue about how these galaxies work. Stars are powered by nuclear reactions that turn hydrogen into helium. A star like our Sun can do this for about 10 billion years. But bigger, bluer, hotter stars use up their fuel much faster. They have shorter lives and eventually blow up as supernovas. In places like the Orion Nebula, we can see gas turning into stars, including many blue stars that must have formed very recently. When these stars die, they release material back into the gas between stars. New stars can then form from this recycled gas. So the cool gas and young stars are part of a cycle. It makes sense that galaxies without gas clouds also don't have young stars. Galaxies are not just held together by gravity, but are also connected chemically. The atoms in our bodies come from all over the Milky Way, but few come from other galaxies. All the heavy elements like carbon, nitrogen, oxygen, and iron in the solar system must have been made by earlier generations of stars that lived and died before the Sun formed. The process of stars forming, living, dying, and being reborn in our galaxy is like an ecological cycle. In this cycle, spread out gas and stars have a mutually beneficial relationship. This ecological comparison shows other aspects of galaxies. They are complex, constantly evolving, and relatively isolated. However, the recycling of matter between stars and gas is not perfect. Some of the gas that becomes stars gets permanently trapped, meaning it becomes part of long-lived low-mass stars or black holes. Elliptical galaxies lack young stars, while ongoing star formation in other galaxies makes them disk-shaped. Galaxies likely begin as turbulent gas clouds contracting under gravity. As these clouds collapse, gas globules merge into a rotating disk, but only if not all gas turns into stars first. Stars that form before the disk settles have random orbits, typical of elliptical galaxies. The efficiency of gas turning into stars determines galaxy types. Elliptical galaxies formed most stars billions of years ago, while disk galaxies continue forming stars today. Disk galaxies are like slow metabolisms, still holding onto gas for future stars. Irregular galaxies, such as the Magellanic Clouds, have even less gas incorporated into stars. The spiral arms in certain disk galaxies highlight areas where stars are forming rapidly. These arms appear like persistent wave patterns, but we're still figuring out what causes and maintains them. Some disk galaxies, called exogalaxies, don't seem to have gas. They're often found in galaxy clusters and might have lost their gas through interactions with other galaxies. While most galaxies are disk-shaped or elliptical, some appear disturbed due to interactions with other galaxies. These interactions create tidal forces, similar to how the Moon and Sun cause tides on Earth, pulling out dramatic bridges and tails of stars and gas. These disturbances can trigger star formation by creating strong shock waves. Imagine if we could experiment with galaxies in a lab, testing how they react to different conditions. Interestingly, nature has already provided us with such experiments through interacting galaxies. While these interactions are rare in our recent universe, they were more common in the past when galaxies were closer together. Recent findings from the Hubble Space Telescope suggest that violent galactic interactions were frequent in the early universe. When galaxies interact closely enough, they're expected to merge. This merger can disrupt the spiral structure of two galaxies, creating a more rounded, elliptical shape. It's possible that some elliptical galaxies form through this process. Stars, like individual organisms in a galactic ecosystem, go through a life cycle from birth in gas clouds to their eventual end. We understand why stars have the properties they do. However, the question of why galaxies exist is more complex. Galaxies formed in the distant past, and we're unsure how much of their formation can be explained by ordinary processes versus exotic conditions in the early universe. For example, why are most galaxies similar in size? There may be underlying physics that determines the size of galactic clouds, similar to what we know about stars. The scales of galaxies are influenced by the early universe's conditions, which allowed gas clouds to condense into galaxies. Yet, there's still much we don't understand, like why individual galaxies end where clusters of galaxies begin. Simple calculations suggest that massive turbulent gas clouds couldn't cool and fragment into stars beyond a certain size, which may explain why galaxies have a maximum mass and size. Eddington once suggested that a physicist on a cloud-bound planet could forecast the properties of stars. But when it comes to galaxies, we're still searching for those confident predictions. To truly unravel the mysteries of galaxies, we need to place them within the vast framework of the cosmos, tracing their origins back to the early universe. What's truly captivating, and somewhat puzzling, is that a significant portion, up to 90% of a galaxy's mass, remains shrouded in mystery, existing in an enigmatic dark form. This dark matter wields immense gravitational influence, shaping galaxies from their outer edges to their very cores. It's a cosmic conundrum that keeps astronomers intrigued and searching for answers. Imagine looking at a galaxy and realizing that what you see, stars and gas, is just a tiny part of its total mass. There's something invisible, called dark matter, that outweighs everything we can see by a large margin. This idea isn't new. It goes back over 60 years when scientist Fritz Zwicky saw that galaxies in the Coma cluster lacked enough visible mass to hold together. We're pretty sure dark matter exists, but we're still not sure what exactly it is. It's like a cosmic puzzle waiting to be solved. Our Milky Way and similar spiral galaxies, like the Andromeda Galaxy, seem to be surrounded by halos of dark matter that stretch far beyond their outermost stars. One way we detect these dark matter halos is by studying how fast the galaxy's disk rotates at different distances from its center. We use clouds of neutral hydrogen as markers for this motion. In galaxies seen almost sideways, like Andromeda, radio telescopes help us measure the speed of this gas. Normally, if only visible matter influenced the gas, its speed would decrease as we move away from the galaxy's center. However, the gas maintains a steady speed, indicating that it's affected by a larger mass than what's visible. This scenario is akin to finding Pluto orbiting the Sun as fast as Earth, suggesting an invisible mass beyond what we can see. Similar measurements for many galaxies suggest that dark matter could make up at least 5 times the mass of the visible disk. Further evidence for dark matter in our Milky Way comes from studying the velocities and orbits of dwarf satellite galaxies and globular clusters in its halo. By calculating the total mass of the local group, which includes our galaxy and Andromeda, we find that there must be enough mass to explain why Andromeda and our galaxy are moving towards each other. This suggests that the halos of our galaxy and Andromeda might merge due to their immense mass. Elliptical galaxies also show evidence of extended dark halos, but the signs are different. In these galaxies, the gas is extremely hot, preventing it from condensing towards the center or forming a disk. This hot gas emits X-rays, allowing us to study its temperature distribution. Even at great distances from the galaxy, the gas remains so hot that it would escape the galaxy's gravitational pull if not for an additional gravitational force, likely from dark matter. Thus, elliptical galaxies, like disk galaxies, must possess extensive dark halos to explain this phenomenon. Galaxy clusters harbor vast amounts of dark matter, far exceeding the visible matter within galaxies. To maintain stability, the cluster's gravitational pull must balance the galaxy's relative motions. By measuring galaxy velocities, we estimate the cluster's total mass, consistent with the virial theorem. X-ray and gravitational lensing studies offer complementary insights into the distribution of mass within clusters. Gravitational lensing distorts background galaxies' images, aiding our understanding of dark matter's influence on cluster dynamics. Conservatively, dark matter in our galaxy might be small stars like brown dwarfs or Jupiters, each less than 7% the mass of our Sun. Although they emit little light, they could be spotted through gravitational lensing, occasionally magnifying background stars. Detecting them requires precise alignment between the dark object, background source, and Earth. These brown dwarfs might create magnified images of distant stars, too small for current telescopes to resolve. Still, we can detect them by watching for symmetrical changes in magnification as they pass in front of background stars. Even if all the dark matter in our galaxy's halo came from low-mass stars, the chance of significant gravitational lensing along a typical line of sight would be extremely rare, about 3 in 10 million. Astronomers would need to monitor millions of stars to detect this. Recently, two groups have identified nearly a dozen potential lensing events, but these efforts suggest that brown dwarfs alone cannot explain most of the dark matter in our galaxy's halo. Another proposed dark matter candidate is very massive objects, or VMOs, potentially black holes with masses from 1,000 to 1 million times that of our Sun. However, detecting VMOs through gravitational lensing is difficult due to slower and less frequent events compared to brown dwarfs. It might take decades of surveying before even a single event is detected. Computer simulations of galaxy formation provide valuable insights into the nature of dark matter. Given that 90% of a galaxy's gravitating material is dark, understanding the properties of dark matter is crucial for understanding how galaxies form and cluster. By making assumptions about the conditions shortly after the Big Bang, scientists can model how clustering evolves over time and compare these simulations with observations. We'll delve deeper into these simulations later when discussing the potential formation of supermassive black holes. But for now, let's focus on exploring the fascinating processes occurring at the centers of galaxies. In a galaxy, the concentration of stars noticeably increases toward the center, known as the nucleus. The nucleus of the Milky Way is obscured at visible wavelengths by a thick veil of dust and gas, but infrared observations have revealed as many as 1 million stars within the innermost single light year. In comparison, the concentration of stars near us is about 1 sun per 167 cubic light years. On average, stars are 300 times closer together in the galactic center than they are in the vicinity of the Sun. The nuclei of galaxies appear to be rather dangerous places, where stars are not only densely packed but also move randomly at speeds of up to several hundred kilometers per second due to their mutual gravitational attractions. The only other places with such high stellar densities are the centers of globular clusters. But there, the random velocities are 10 to 100 times slower. Some astronomers speculate that galactic nuclei form from the coagulation of globular clusters. Violent collisions between stars are inevitable in galactic nuclei and are predicted to occur about once every 10,000 years in the nucleus of the Milky Way. Predicting what happens to a dense cluster of stars in the center of a galaxy is hard and has been debated since the 1960s. One problem is that we don't fully understand what happens when two stars get very close to each other. Usually, we think of stars as tiny points when looking at a whole galaxy, But this doesn't work for close encounters. When two stars pass very near each other, tidal forces change their shapes, heat them up, and slow them down. If they slow down enough, they might start orbiting each other and become a pair, called a tidal capture binary. If the tidal forces are strong enough, the stars might eventually merge into a single, more massive star. What happens to this new star depends on how the merger occurs and the stages of evolution of the merging stars. Stellar evolution theory helps us predict a star's future if we know its chemical makeup. This includes not only the overall ratio of hydrogen to helium, but also how this ratio changes with depth. For a star formed by merging, it's hard to determine the initial chemical structure. We can estimate the overall composition by adding up the contents of each original star, though some mass might be lost during the merger, making this estimate uncertain. The variations in composition with depth are affected by complex mixing processes that are difficult to predict. The best way to understand the merger process is through computer simulations. These simulations are still developing, but are becoming more advanced rapidly. When two stars meet at low speeds compared to the escape speed from their surfaces, they are likely to merge into a single star. For example, the escape speed from the Sun is 618 kilometers per second. At higher speeds, the stars crash into each other and send out high-speed gas plumes. Low-speed collisions create bigger stars, while high-speed ones destroy them. Predicting exactly what happens, including how much mass is lost, needs computer simulations. Collisions mainly cause destruction in clusters where stars move very fast, over 1,000 kilometers per second. In the Milky Way's central star cluster, stars move at about 200 kilometers per second, so they usually merge. This likely explains the many massive blue stars in our galactic center, formed from such mergers in the last million years. Stellar encounters will definitely impact the evolution of a galactic nucleus, but we don't yet know exactly how. If many stars merge, the average star in the cluster would become slower and more massive. This would make gravity pull the star cluster closer together, causing the stars to move faster, as the virial theorem predicts. As the star's random speeds increase, we might see a shift from a nucleus where most encounters cause stars to merge to one where most encounters cause stars to collide and break apart. During the phase where stars merge, other important things happen. Adding mass to a star makes it live shorter and die more violently, so more supernova explosions would occur with more massive stars. These explosions throw matter out of the nucleus, reducing its mass and weakening its gravity, which might stop or reverse the cluster's contraction. Supernovae would leave behind neutron stars and black holes, which are less likely to collide but still interact through gravity. Weak gravitational interactions would push most stars farther out, leaving fewer in the center, creating a core halo structure. The cluster's fate depends on direct collisions, weak gravitational encounters, and explosive mass loss. One possibility is that coalescence leads to a few huge stars that merge and form a black hole. Another is that a small part of the cluster contracts into a dense core with mostly destructive collisions. When a galactic nucleus starts having stars collide and break apart, its future becomes even more uncertain. Unlike matter thrown out by supernova explosions, the debris from these collisions can't escape the cluster's gravity. Most of it gathers at the cluster's center. In 1966, scientists suggested that this debris could form new stars, which would be denser and faster moving than the original ones. These new stars would eventually collide again, and the cycle might repeat. Whether stars can form efficiently in such a chaotic environment is unclear, but it's likely that a dense gas cloud would form in the center of the collision-prone nucleus. Once this cloud starts shrinking due to its own gravity, it's almost certain to collapse into a black hole. To complicate things further, We can't view a galactic nucleus as a closed system. Explosions from supernovas or strong winds from stars can push a lot of the gas and debris away from the center, stopping it from building up. This is more likely to happen in smaller, slower-moving galactic nuclei like the center of our Milky Way, which has only a few million times the mass of the Sun. But in bigger or denser galactic nuclei, which can have billions of times the Sun's mass, the gas and debris tend to gather. Some of the gas that's far from the center, whether it's from stars in the galaxy, taken from outside the galaxy, or left over from when the galaxy formed, will eventually drift toward the center as it loses speed. Once it gets there, it has nowhere else to go and just piles up. What happens to all this accumulated gas? Will it make more stars, adding to the crowded central star cluster? Or will it gather into a shapeless cloud of gas, pulling on the paths of passing stars and making them collide more often? Could it shrink under its own gravity to become one giant star that's so unstable it collapses into a black hole all at once? We can only guess at the answers to these questions, but it wouldn't be surprising to find extremely massive black holes, perhaps millions or even billions of times the Sun's mass, in the centers of many galaxies. Given the complexity of the situation, the best approach is to rely on what we see. So, what's happening in the center of our galaxy, the Milky Way, which is about 25,000 light-years away? Even though most of the light from the galactic center is blocked by gas and dust, we can still study it using radio, infrared, X-ray, and gamma-ray waves. What we see there is quite chaotic. There's a dense cluster of stars surrounded by a jumbled mess of gas filaments, disks, and blobs. At the heart of it all is a small radio source called Sagittarius A star. The debate about whether there's a black hole at the center of our galaxy was settled when the Event Horizon Telescope captured an image of one. Now we can confidently say we've found really huge black holes in other galaxies. Some are almost 1 billion times the mass of the Sun, far bigger than any black hole in our own galaxy. They create the brightest events in the universe, the quasars. And we can also find them by seeing how they affect the movements of stars and gas in galactic centers. Imagine the thrill astronomers must have felt when they first realized that beyond our Milky Way, there existed vast island universes of stars and gas, each with its own story to tell. But as they delved deeper into these cosmic realms, they stumbled upon a mystery. The centers of many galaxies seemed to harbor secrets, strange intense concentrations of blue light that defied explanation. This light wasn't like anything seen before. It blazed with a brilliance far beyond that of normal stars and gas. Its spectrum shimmered with an excess of blue and ultraviolet radiation, leaving astronomers scratching their heads. How could such light be produced? It was clear. These weren't your average galactic residents. Some of these central sources of energy outshone entire galaxies, their brightness fluctuating mysteriously over time. These enigmatic galaxies earned the title of active galaxies, and their cores were dubbed active galactic nuclei, or AGNs for short. And then there were the outliers, the quasars, the most extreme examples of these cosmic powerhouses. But the strangeness didn't end there. Radio observations unveiled a new layer of peculiarity. Narrow lightning-fast jets of gas shooting out from these cosmic behemoths, defying conventional wisdom. In this cosmic theater, where galaxies became more than just collections of stars, they became cosmic powerhouses, their centers ablaze with energy and mystery, inviting astronomers to delve deeper into the secrets of the universe. Figuring out active galaxies and quasars was like solving a tricky puzzle. The discovery of active galactic nuclei was a lucky break, even bigger than finding pulsars. It took unexpected findings by radio and optical astronomers to reveal these powerful events, possibly linked to massive black holes in galaxies' centers. Hints of unusual activity in galaxy centers appeared long before quasars were discovered in 1963. Around 1917, astronomers noticed a jet-like feature in the nearby galaxy M87, but didn't follow up on it. Other galaxies, like M82, showed signs of disruption, but it turned out to be due to hyperactive star formation, not a black hole. During 1940s, Carl Seyfert at Mount Wilson Observatory observed that some spiral galaxies had intense blue nuclei. These Seyfert galaxies emitted strong emission lines indicating ionized gas, but with lines smeared over a wide range of wavelengths, suggesting extreme turbulence. In 1954, radio astronomers changed the game. They were studying a strong radio wave source called Cygnus A, the second brightest object in the radio sky. Before, astronomers only knew something was emitting lots of radio waves, but not what it was or how far away. Bard and Minkowski connected Cygnus A with a faint galaxy with a redshift of 0.05, making it about 300 times farther than the Andromeda Galaxy. This distant galaxy turned out to be the source of the radio waves. If a galaxy so faint invisible light could produce such strong radio signals, it meant that some unusual galaxies might be detectable by radio, even if they were too far away to see with optical telescopes. The dim picture of Cygnus A looked like two parts joined together, which astronomers interpreted as two galaxies crashing into each other. Then, astronomers from England's Nuffield Radio Astronomy Laboratories found something surprising. They discovered that the radio waves from Cygnus A didn't come from the galaxy itself, but from two huge patches on either side of it in the sky, each about 250,000 light-years away. These radio patches look like a dumbbell in 3 dimensions and are called lobes. This double radio structure is common in strong radio sources. This discovery made astronomers rethink their idea about the collision of galaxies. It turned out that the illusion of two parts in the optical image was caused by dust. But the question of where the radio waves came from became even more mysterious. Back in the 1950s, scientists understood that radio waves from space were produced by something called synchrotron radiation. This happens when electrons move really fast in magnetic fields, like what's seen in the Crab Nebula. To make as much synchrotron radiation as we see in the lobes of Cygnus A, there must be a lot of energy stored in fast-moving electrons and magnetic fields. But how much energy is that? In important papers from 1956 and 1959, an astronomer calculated that the total energy in the lobes of a big source like Cygnus A must be greater than the energy released by totally destroying 1,000,000 solar masses of stuff. The discovery hinted that the centers of galaxies can release huge amounts of energy, much more than even a supernova explosion. This energy turns into fast-moving particles and strong magnetic fields. But where does all this energy come from? Some scientists thought that these exploding galaxies might be where new matter is being made, as suggested by a theory called the steady-state theory of the universe. According to this idea, the universe stays mostly the same over time because new matter is continuously created. However, this theory isn't widely accepted anymore because we now have evidence that the universe started expanding from a fixed point in the past. Despite this, the idea was forgotten when the steady-state theory lost popularity. Other ideas were thrown around too, like suggesting that galactic centers might be giant reactors where matter and antimatter are annihilated. But nobody thought about black holes yet. Quasars weren't spotted earlier because they looked a lot like regular stars. Their true nature was only uncovered through careful study using spectrographs, after their radio signals were detected by chance. This discovery reflects John Herschel's idea from 1820, where he suggested that new kinds of celestial bodies, holding crucial secrets of the universe, might hide among tiny stars, indistinguishable from the rest. Most scientists think that quasars are just very bright versions of the same blue cores Seyferts saw in nearby spiral galaxies. The reason they seem like solitary stars to us is because they shine so brightly that they overshadow their surrounding galaxies, making them invisible. Although many early found quasars emitted strong radio signals, it turns out that this is unusual. In fact, most quasars with bright, broad emission lines don't emit much radio waves at all. Quasars looked like regular stars, so they went unnoticed for a while early quasars mostly emitted strong radio waves. It turns out that this is not typical. In fact, most quasars with bright, broad emission lines don't emit much radio energy. Some galaxies, like quasars and Seyfert galaxies, shine really bright in different kinds of light, while others, like Cygnus A and M87, also known as Virgo A, mainly release energy as radio waves. Astronomers group them into different types, but sometimes the names they use aren't very imaginative. Instead of fancy names, they just use terms like Type 1 and Type 2 for Seyfert galaxies, or Fanneroff-Rayleigh types 1 and 2 for radio galaxies.
Quasars, Seyferts, and radio galaxies are all called active galactic nuclei. But are they really similar? Even though spiral and elliptical galaxies seem different, they share basic traits as systems of stars and gas held together by gravity. Grouping them as galaxies helps scientists find common rules. But does the term active galactic nucleus mean they are deeply connected?
In these galaxies, all the action happens in the nucleus. This is clear for quasars and Seyferts because of their bright, compact nuclei. We'll see later how this connection is also true for radio galaxies, but it goes deeper than that. The similarities between different types of activity suggest they're all just different versions of the same thing. We can group these similarities into 4 categories. First is high energy output. These galaxies can emit energy at a crazy rate. The brightest quasars and radio galaxies can be over 100 times brighter than all the stars in a big galaxy put together. The second category is long-lasting activity. Their activity can last for millions of years, making them the longest-lasting phenomena in the universe. Third one is compactness. These galaxies are really compact. For example, the brightness of the quasar 3C 273 changes a lot in just a month. They can change rapidly, sometimes in just a few hours. This rapid change tells us they must be small, because nothing can change faster than the speed of light. The fourth characteristic of AGN is their ability to accelerate gas to near the speed of light within the gravitational field near a black hole. Think of it like this. Imagine you're at a cosmic fireworks show. While most fireworks explode in a burst and fade away quickly, these galactic fireworks are like the grand finale. They keep going and going. Now, let's talk about the radiations of active galactic nuclei. It's different from what stars or gas normally produce. While AGNs shine brightest in one part of the spectrum, they also emit a lot of radiation across a wide range of wavelengths. Some AGNs emit similar amounts of power in the radio, infrared, optical, ultraviolet, X-ray, and gamma-ray parts of the spectrum. That's a huge range. Stars and gas, on the other hand, usually emit most of their radiation in a narrow range of wavelengths, depending on their temperature. This kind of radiation is called thermal. But AGNs have non-thermal spectra because their power is spread out across so many wavelengths that you can't assign a temperature to it. And with this, we are going to enter into the paradox of the black holes. Active galactic nuclei likely originate from massive black holes at galaxy centers. AGNs can produce energy comparable to or greater than a whole galaxy within a solar system-sized area. This aligns with the gravitational forces near black holes and explains high-speed gas streams and non-thermal radiation spectra. Though details are still debated, the black hole theory is straightforward. AGNs change brightness quickly, indicating a small size. The mass and size measurements give a mass-compactness ratio, revealing gravitational strength. This ratio's theoretical maximum, defined by the speed of light and gravitational constant, suggests that if an AGN's mass compactness is near this limit, it is likely a black hole. This comparison helps identify black holes in the universe. To estimate an AGN's size, we observe how quickly its brightness changes. The source size must be smaller than the distance light travels in that time. To estimate the mass, we use Einstein's E=mc². The total energy an AGN emits over its lifetime helps calculate the mass converted into energy. Efficiency varies, with nuclear reactions around 1% and matter falling into a black hole up to 40%. The remaining mass stays in the nucleus due to gravity. Astronomers estimate an AGN's lifetime energy output using two methods: calculating the energy for strong radio sources and multiplying current brightness by the AGN's age. They estimate the age using the fact that about 1% of galaxies are active at any time, suggesting AGN last at least 100 million years. By calculating total energy output and assuming 10% efficiency, they estimate the mass processed, with at least half remaining in the AGN. We can estimate an AGN's mass from its brightness using the Eddington limit, the maximum brightness a mass can have without radiation blowing matter away. Since AGN don't fall apart, their brightness is below this limit, giving us a lower mass estimate. Bright quasars or powerful radio galaxies likely have central masses of 100 million to a few billion suns, while less bright Seyfert galaxies have lower masses. AGN's mass compactness suggests black holes but doesn't conclusively prove it.
However, this raises the question: can supermassive stars produce active galactic nuclei?
Supermassive stars likely can't sustain AGN. Stars over 100 solar masses, balanced by radiation pressure near the Eddington limit, are unstable and quickly form black holes. Black holes are a more efficient power source for AGN. Powerful and long-lasting objects like quasars and strong radio sources are best explained by black holes. Other AGN, like starburst nuclei, might be early stages leading to black holes. Not all collapse paths are understood, especially for rapidly rotating supermassive stars, but most scientists agree that quasars are powered by black holes of 100 million solar masses or more. These black holes are fueled by gas from their galaxy or swallowing stars. As debris spirals in, it accelerates to near light speed, releasing gravitational energy that powers AGN's brightness and jets. Imagine a quasar's energy 10 trillion suns within Earth's orbit, with bursts and lulls in hours. This aligns with black hole physics. In the past, such phenomena puzzled scientists, but today, they are understood through black hole interactions, a consensus reached after decades of study. In the 1960s and 1970s, the idea that black holes powered quasars was debated, but now it is widely accepted. The big debate was whether quasars were truly distant super-bright objects. Some astronomers questioned the application of Hubble's law, which links distance to redshift, suggesting quasars might be closer and less powerful. A group of scientists proposed that quasars were ejected from nearby galaxies, citing connections between high redshift quasars and low redshift galaxies. They found gas and stars linking galaxies to quasars. However, if this idea were correct, we would see some quasars with a blue shift, which hasn't been observed. Some scientists proposed new ideas to explain quasar redshifts, noting unusual data patterns. However, With data from over 10,000 quasars, many patterns weakened. Without a clear predictive theory, these anomalies don't strongly support unconventional views. The quasar debate was intriguing for its scientific and perspective clashes. Some believed quasars fit known physics. Others hoped for new physics. Most astronomers now agree quasars are distant, supported by their clustering with galaxies and gravitational lensing. These findings convinced many skeptics, but not all, showing the dynamic nature of science. Quasars remain mysterious, much like other astrophysical phenomena. Understanding them is complex and slow due to their intricacy and limited researches. Early pioneers like Geoffrey Burbidge and Edwin Salpeter laid the groundwork for understanding quasars' immense energy needs and supermassive collapsed objects. But progress has been gradual. Discovering quasars early on delayed consensus, which might have formed quicker if found alongside pulsars and X-ray sources. While new laws in galactic nuclei are possible, we should avoid complacency. Historical debates, like over binary stars, show that our understanding evolves. Most astronomers now accept quasar distances based on redshifts, but surprises are always possible, as with the discovery of distant galaxies and nearby gas clouds once thought to be nebulae. Now with this we are going to move to another part of this video, which we will delve more into the paradigm of quasars. But if you have watched the video till now, then you must have gained something from my efforts, and if you do, I kindly ask you to subscribe and like the video. Understanding supermassive black holes' interactions with matter to create active galactic nuclei is complex. We are progressing but lack a complete model. Black holes emit intense light in two main ways: by accumulating mass, like X-ray binaries, or by using electromagnetic processes to tap into their spin energy, acting like a flywheel with surrounding matter slowing its spin to release energy. This might produce jets, with both methods potentially occurring simultaneously. AGN characteristics depend on the balance of these mechanisms, influenced by mass accumulation rate, magnetic fields, and black hole spin. Other factors include the black hole's mass and host galaxy properties. The goal is a unified model explaining all AGN, akin to theories for different star properties. Accretion in X-ray binaries and AGN share similarities. In X-ray binaries, mass from a companion star fuels the process, while in AGN, the source of accreted matter is uncertain. It could come from interstellar gas in the galaxy, gas captured during galactic encounters, or gas released when stars get too close to the black hole. Regardless, the gas likely forms an accretion disk due to its angular momentum. Accretion disk theory predicts the radiation spectrum emitted by such disks around black holes of different masses and with varying accretion rates. While X-ray binaries emit radiation mainly in the X-ray range, AGN accretion disks are predicted to peak in the ultraviolet range. Observing this directly is challenging because dust and gas absorb much of the ultraviolet light. However, there are indications that quasar spectra show an ultraviolet bump, possibly originating from the accretion disk. AGN spectra are complex, involving various processes across different wavelengths. Infrared radiation likely comes from heated dust, X-rays from a turbulent corona above the disk, and radio and gamma rays from accelerated gas jets. Reprocessing further complicates things, as radiation emitted in one form can be transformed into another. Identifying primary sources of radiation becomes challenging due to these intricate energy conversions. The central engines of highly active galactic nuclei may share similarities. They likely derive power from both accretion and the spin of black holes, with variations depending on the galactic environment. Despite extreme conditions, the relevant physics is understood, posing the question: how much power comes from accretion versus the black hole's spin, and in what forms does it manifest? These calculations are akin to nuclear physics in stellar modeling. While evidence linking black holes to AGN is circumstantial, so were beliefs in nuclear energy powering stars before solar neutrino detection. Yet, comparing theoretical models with observations is more ambiguous for AGN. Unlike stars where energy reaches the surface steadily, in AGN, it's reprocessed across the electromagnetic spectrum, influenced by the host galaxy's environment in poorly understood ways. In science, we often build models based on data and then test them. This works well for some fields like particle physics, where basic equations rule. But in complex sciences like geophysics, models might not explain every detail. For example, while concepts like continental drift help, they can't explain everything about continents' shapes. Looking forward in quasar research, progress won't just come from theorists. Instead, new technology often leads the way. Throughout history, astronomy has relied on new tools and inventions. Today, powerful telescopes and radio detectors help us study things like active galactic nuclei. Sometimes, technology moves faster than our ability to understand it. Models we create might become outdated when new data arrives, but this cycle of improvement drives our understanding forward. For example, we've learned a lot about cosmic jets thanks to advancements in radio astronomy. This shows how new tools can change our view of the universe. Now, let's explore the next section, which delves into a central aspect of black holes. In the depths of radio galaxies, powerful jets of gas shoot out, extending millions of light years into space. It's surprising because these galaxies likely contain black holes at their centers, and black holes are typically seen as cosmic vacuum cleaners, pulling everything in. The notion that gas heading toward a black hole can be propelled outward at nearly the speed of light challenges our expectations. This concept would have seemed unbelievable before the era of radio astronomy, which has often revolutionized our understanding of the cosmos. Jets, first observed in radio galaxies, are a widespread occurrence in the universe. They typically arise when gas with significant angular momentum spirals into a gravitational field, like at the core of an accretion disk. Picture them as cosmic whirlwinds. These phenomena emerge across various systems, including radio galaxies, X-ray binaries, and young stars. Hence, they aren't exclusive to black holes. However, the jets formed near black holes exhibit characteristics unique to the extreme conditions around them. Nowhere else do we witness matter propelled at such immense velocities, sometimes nearing the speed of light. Radio astronomers rediscovered jets from active galactic nuclei. In 1917, Heber Curtis observed a visible light jet emanating from the nucleus of the galaxy M87. However, it wasn't until his 1918 publication that he described it in detail, noting its brightness and connection to the nucleus. Unfortunately, this observation wasn't pursued further at the time. This oversight isn't surprising, given that in 1918, it wasn't confirmed that M87 was a distant galaxy. It took another 60 years and the advent of radio astronomy to definitively establish jets as common structures in the universe and understand their true nature. Think of a radio wave source as creating ripples, similar to how a rock creates circular ripples in a lake. A telescope collects information about these ripples by detecting their directions. Imagine being on a rowboat in the lake. If a single ripple passes by, you'll feel the boat move, but won't know where it came from. However, if two rowboats are far apart and feel the ripple at the same time, they can determine the direction of the rock by comparing their observations. In a telescope, this comparison is done through interference, where positive and negative displacements of each wave are combined. This process amplifies the signal when all parts of the telescope receive waves from the source simultaneously. In radio astronomy, we deal with a series of periodic ripples, spaced by a specific wavelength. When these ripples are close together, timing them is straightforward. However, if the ripples are longer, it becomes harder to determine their peaks and troughs precisely. To overcome this, telescopes observing longer wavelengths need to be larger to maintain the same angular resolution as those observing shorter wavelengths. To solve the resolution challenge without constructing huge dishes, radio astronomers employ a clever technique. They compare signals collected across a long baseline or distance between points, allowing them to discern the direction of the waves. This doesn't require merging signals from every point within the baseline. Instead, they can achieve high resolution by combining signals from smaller dishes spaced apart along the baseline, creating what's called an interferometer. Determining the number and arrangement of smaller dishes is crucial in interferometry because directional accuracy varies depending on their configuration. Just as on a lake, where pinpointing the direction of a rock is easiest if the rowboats are evenly spaced around it, in a telescope, a pair of dishes aligned north-south can best resolve sources lined up in the same direction in the sky. However, widely spaced dishes can capture fine details but may miss large-scale strictures. To create a detailed picture of a radio source, numerous dish pairs with various orientations and spacings are required, which can eventually lead to challenges akin to constructing a single, large dish. In the 1950s, a breakthrough came with the idea of using Earth's rotation to simulate a larger telescope. By rotating with the Earth, pairs of dishes in radio telescopes altered their orientation relative to the sky, effectively creating a more comprehensive view of celestial objects. Over the following decades, larger interferometers were constructed, such as the Very Large Array in New Mexico, consisting of 27 telescopes spread over 40 kilometers. These telescopes could reveal details as small as a dime at a distance of 20 kilometers, rivaling the Hubble Space Telescope's resolution. Interferometry experiments showed that the majority of radio emissions from galaxies like Cygnus A originated from symmetrical lobes on either side of the galaxy, indicating a common feature among powerful radio galaxies. This suggested that whatever generated these lobes was expelled symmetrically from the galaxy. The more advanced radio telescopes picked up on extra features. In the brightest double radio sources, like Cygnus A, they often identified hot spots, compact areas emitting strong radiation. Many of these bright sources also displayed tails or bridges of weaker emissions stretching from the hot spots towards the center, where a concentrated burst of radio waves, known as a core, typically resides. Most double radio sources are linked to elliptical galaxies or quasars, with their core typically aligning with the optical center of the galaxy. This newfound wealth of detail posed challenges for theorists trying to explain double radio sources. Initial theories suggesting the lobes were massive clouds of extremely hot, magnetized gas, ejected in enormous explosions, lost favor when it became apparent that their energy would dissipate as they expanded, leaving insufficient energy to account for the observed radio emissions. Some proposed that the hot spots themselves might fuel the lobes, perhaps from black holes within them flung out by gravitational forces. While creative ideas emerged, explaining the high level of symmetry and alignment remained elusive. The breakthrough came with the detection of central cores. The discovery of radio emissions from the core hinted at ongoing activity at the galaxy's center. Scientists speculated on a continuous energy supply to the lobes, solving the mystery of how expanding lobes regained energy and explaining their symmetry. But how could this energy travel precisely across vast distances? Various ideas were explored, but none seemed effective until researchers at Cambridge University proposed a solution in the early 1970s. Twin streams of fast-moving gas generated in the galaxy's nucleus and moving in opposite directions into the lobes. Understanding how the lobes and hotspots form requires considering that galaxies are not isolated but surrounded by interstellar and intergalactic gas and dust. When activity starts at the galaxy's center, jets of gas emerge, akin to water from a hose. These jets pass through the interstellar and intergalactic medium, which resists their expansion. Despite the decreasing density of surrounding matter, the jet's end moves slower than the gas inside, as it pushes surrounding matter out of the way. And thus, we have reached the conclusion of the initial segment of our series. Stay tuned for the next segment of our thrilling video series as we explore the mysteries of black holes in greater depth. Be ready for the launch of our upcoming video, and in the meantime, show your support by liking, commenting, and subscribing to our channel. Your engagement will truly elevate our content